Hey folks, welcome back to the series on AI paper reviews. It's been a minute since I've made a video, and a lot has happened in the world of AI. GPT-5, a lot of Chinese models, Claude 4.1, and so on and so forth. So it'll take me some time to ramp up, but thank you for your patience. But this week I've got three interesting papers, so we'll begin with that. I've got a bunch more papers that I'll try to be more frequent with these updates, but it's just you don't get a lot of time to review all these papers. Okay, we can get started. So the first paper that I want to talk about is a small modification to GRPO, which is this GSPO, Group Sequence Policy Optimization. This was recently produced by the Quen team, and let's quickly go into the summary of this paper. So first of all, let's revisit the GRPO loss. So in GRPO, we have this important sampling part. So for each token, we compute the probability of the token on the policy model with respect to the old one, like it's an off policy setting. And then you have the advantage, which is just like your score minus the variance, and then it's clipped. That's the small addition that PPO introduced. So here, GRPO is basically like, let's say your rollout was successful, you get some reward. So in GRPO, all tokens, because it is at a token level, all tokens get the same reward. So all tokens of my sequence get the same reward. This is what this paper claims that is wrong with GRPO. This leads to instability, and this leads to like higher variance because it's a sequence level reward, but you're giving it to per token. And that's the problem with GRPO, as they claim. They introduced GSPO. It's a modification to GRPO where the reward is given to sequence. So let's go back to GRPO. Here you will see that there was a sum over tokens. So all the tokens of a sequence. And when we go to GSPO, that sum is missing. This G is all the rollouts, but that sum over tokens is missing because now we don't give the reward to all the tokens. We just compute a sequence level probability distribution. And the way it is defined is, so this SI is basically just my probability of my entire sequence. So sum of logs is product of logs, so probability of the entire sequence. And then this is length normalized, and then this can be encapsulated in this form. So basically now you compute the probability of the entire sequence, and so you kind of produce a sequence likelihood, and the reward or advantage is given at a sequence level. So that's the main difference, and they say that this works much better than GRPO. As you can see, the reward for GSPO trends higher quickly, and they also say that this is useful for the MOE setting, because in MOE there's a lot of instability because you need to capture what experts were routed in the original in your pi old, and then you need to make sure the new one gets the same trajectory of expert selection. So you have to develop these strict routing replay kind of algorithms, which you don't need to do in GSPO because you're working at a sequence level. You don't care so much about the tokens. It's not at a token level, and that's the benefit. So this is like a modification of GSPO, which they believe works well. Yeah, I'll leave it at that. Again, this is a summary. If you want to read more, just look at the paper. Okay, the other paper, an interesting one that came out of ASU, is chain of thought reasoning of LLMs, a Mirage, or data distribution lens. In this paper, they argue that the chain of thoughts that we see in our model are a function of what the model has already seen in its pre-training. So if your problem is similar to, or in distribution, so if your problem is similar to the kind of chain of thoughts and reasoning patterns that the model has already seen, it will do well. But as soon as you start going out of distribution, the model starts sucking. So their claim is that CoT is largely driven by training distribution, and CoT reasoning is brutal and it vanishes when it's pushed beyond training distribution. So they create like a simple test setting where there are simple tasks, and these are decomposable tasks. So let's say here F1 is a rotational transformation, F2 is a cyclic shift. Now you can like combine them together or compound them together to make complicated settings. So if this thing is in distribution, like you combine two, and that's equal to just two combined, then you can also have like out of distribution kind of setting. So basically they will train the model on a particular task, and in test they will give some out of distribution combinations, and they see how well the model generalizes. So they're looking for reasoning steps like this, like how the model breaks down reasoning into how it applies these compositional objects. I'll quickly just look at the results. So here, like for example, if the model was trained on these kind of tasks, so this is train and test. So it was trained on F1, composition of F1s, the accuracy is pretty good. But if it was trained on composition of F1 and F2, and then I ask it to test on F1 and F1, it just fails. Same thing the other way. So there is some reason to believe that. So here you can see how if it's in distribution, the performance is 100, and as soon as you start going to out of distribution, you need more and more data to recover accuracy. And this also ties into like how RL helps, because RL tends to help the model generalize. SFT helps it memorize, RL generalizes, so this is kind of in the same vein. Take a look. This is an interesting like case study. Take a look at this paper. I thought this was interesting. Finally, for this video, the last paper that I want to discuss is this new Falcon-H1, which is a hybrid reasoning model which combines both SSM, which are like Mamba-like state space models, and attention. And they've been able to finally make a flagship model that is competitive with the transformer models. So let's look at the architecture. So so given an input sequence, typically in your transformers you have like attention heads. Here, instead of having, let's say, n attention heads, they would have n over 2 attention heads, and then n over 2 state space heads. And then finally, they would concat the results. So that's the difference. Instead of having just state space or just attention, they have like a hybrid, and they do a lot of ablation on the ratios and so on. And so this is mostly the model. Again, because it's a different kind of architecture, you have to do scaling laws, you have to figure out the right hyperparameters and all. And that's what the paper dives deep into. What is the attention fraction and how does the loss vary? What is the SSM fraction and how does the loss vary? And all these ablations. So this is a pretty good paper from that respect. But the main idea is what I said it was. And then let's finally look at the results. Let's see. That's a big paper. And obviously they had to do a lot of innovations to get it to run efficiently. So let's look at the 1.5B model, and as you can see, it's pretty competitive with the other 1.5B models. Now the issue with this result, so what they show is the models are pretty competitive, sometimes even like beating all the dense models out there. But issue with this is I don't think they've trained all these models from scratch on the same data mix. So I don't know how much of a factor is data here compared to the other models. And that's that's so that makes me wonder, like, it could be both a factor of data and the architecture. But again, the fact that they get pretty good results is indicative of like how good this architecture is. So something to keep in mind and something to watch out for. As these Falcon family of models, which I believe are coming from UAE team, are going all in on this hybrid architecture, and at least there's something other than transformers. So that's good to see. Okay, I think that's all I wanted to cover in this video. Glad I kept it short. And then I will see you guys again next time. Cheers.